Turned you on already.
Okay, so before we start.
Hey everyone, so before we start, this afternoon there's going to be one lecture on the CV components by Nima Sehgal. Then afterwards there's a discussion session. So that's going to take Nima and based on the questions. Lecture, so we're going to divide room in two. One of you are going to go.
Yeah, so the other classroom is called 2B47. The second basement. It's all the way on this end of the building. Okay, just go down the stairs over here, all the way to the bottom, and go as far as you can today. And the wise classroom is around 50%, and should be open. And we'll split the room. Nothing boring now. It's increasingly complicated and messy.
How about
what happens to the lecture spot anyway, okay? Because there's less of them than there is of you, okay? And you keep going until you can type, okay, or it's there.
And then Thursday there's another session where we'll have math and drama.
Okay, so this is my third lecture. I was reminded at the coffee break that actually, if you look at my professional webpage, you can see that I frequently give lectures to students, and I have posted all of these lecture notes on the web, and you can look at my lecture notes and maybe get some insight from them. Not everything I'm talking about here is there, because as I told you, I actually wrote new lectures here, but there's a lot of information there. Okay, so a couple of things that came up from questions that people asked me yesterday. I was talking about Goldstone boson scattering. Goldstone boson goes to Goldstone boson. Let me find the chalk. Okay. So these omegas are Goldstone bosons, goes to omega plus, omega minus. So the amplitude. And I emphasized that there's an equivalence theorem. Real W's. Okay. So first of all, this equivalence theorem has corrections of order mw squared over s. So you may, in some cases, need the subleading terms, mw squared over s. So this only holds at leading order. But the more important point, and it's actually a point for effective field theories too, is that this relationship doesn't hold diagram by diagram. You can't take a diagram with Goldstone bosons and replace them with the longitudinal gauge bosons and expect to get the right answer. It's a scattering matrix element. So you calculate this amplitude and it's equal to this amplitude. But it's not diagram by diagram. You got to do the whole thing. And I think maybe I wasn't as clear as I should have been on that. Okay, so we use these kinds of relationships to look for unitarity violation. We say if we take the Higgs mass to infinity, we get unitarity violation at some energy scale. Or if we take the energy scale to infinity, we get unitarity violation for some Higgs mass. But what does that actually mean? Because we know that these field theories are unitary, right? Quantum field theories are constructed to be unitary. So what that means is that perturbative unitarity is violated. So if you are in a regime where unitarity is violated, it's perturbative unitarity. I've calculated a tree-level amplitude or maybe a loop amplitude. So all that says is that I can no longer trust perturbation theory. It doesn't say the theory is no good. It just says my perturbative expansion is no good and I've got to stop. Okay? So the other question that I got yesterday was about anomalies, which I didn't talk about at all. So the standard model fermions, of course, come in generations. Up, down, left, U right, d right, LL equals mu E. And then copies of the generations, of course, for the second and third generation. And you need a complete generation to cancel the anomalies. You can't just pick and choose, I want a new doublet, I want one of these. You got to have the complete generation with the standard model quantum numbers. So I posted on the Twiki a little explanation of how the cancellation goes between the terms. If people want to work it out, it's kind of trivial and it's also kind of fun. So you can see that the standard model particles have to have exactly the quantum numbers that they have in order to cancel the anomalies. But there's a corollary to this kind of analogy. So I can't just go around and add another generation of quarks because I'm going to have anomalies. But the anomalies have this peculiar feature that left-handed particles and right-handed particles come in with opposite signs. That's the way they work because they're related to the gamma-5 coupling. Okay, so that means if I add some new particle which is identical the left-handed transformations and the right-handed transformations, these are called vector-like fermions. So the left-handed particle transforms identically to the right-handed particle. For those types of particles, the anomalies cancel. So I can add as many of those pairs as my little heart desires when I'm building a model. So it's a favorite model builder's game to add, say, a top partner where the left and right-handed guy transform identically. And I'm free to do that because they don't contribute to anomalies. Okay, so back to Higgs physics. So today I'm going to do a case study in Higgs physics, and hopefully we'll get through it before lunchtime. I like to calculate stuff, so I'm going to work out in detail how glue goes to H works and how it generates an effective field theory. So I have to be very careful not to erase the wrong things. Okay. So actually, can I see a show of hands for how many people have actually done this by hand? Okay, good. So you guys can correct me if I make a mistake. And everybody else can have some fun, because this is super fun. Really, believe me, it's super fun. Okay, so we know that there's no GGH vertex. So gluons come together in a top quark loop here. T, H, P mu A, Q nu B. We'll have some loop momentum, which I'm going to call K. Okay? So I'm going to just calculate this amplitude and then generate the effective field theory. Okay. So we'll start with the resonance formula, which is extremely useful. Sigma hat, the hat means it's Platonic. GG goes to H. It's equal to 16 pi squared over MH, 2J plus 1, 1 over 64, 1 over 4, 2 gamma H goes to GG, delta S hat minus MH squared. Okay, so this is a general resonance formula that works for any resonance producing something of spin J. So J is 0 here. This is the color average. 8 gluons, so 1 over 64. This is the spin average. Okay, anybody want to tell me where that 2 comes from? Yeah, well, actually, it's undoing a symmetry factor, right? Because if I calculate H to GG, I have identical gluons in the final state, so I got to undo that symmetry factor. So that's where it comes from. Okay, so all I have to do is calculate H to GG for that. Okay, so I need to calculate this diagram here, and let me just write it out what it is. Can you see down here? Okay. So I times the amplitude equals minus sign, because it's a closed Fermi loop, minus I GS squared trace TA TB. Okay, these are the color factors here. Okay, minus I, M over V. Okay, I'm just going to use M instead of MT because I'm lazy. So this is the coupling of the Higgs to the top quark. And then there's an integral dnk over 2 pi to the nth. There's some numerator factor, which I'm going to call T mu nu. And there's a denominator factor, which I call D, epsilon mu or P. Okay, there we go. Q, sorry. Okay, so there we go. There's the amplitude there. Okay, the denominator. Okay, the denominator is just the obvious thing. It's k squared minus m squared. K plus p squared minus m squared. K minus q squared minus m squared. And I have to say, I've done this so many times in my life, I could probably even do it without a piece of paper. Okay, so there's the denominator. We're going to combine the denominators using Feynman parameters. Okay, and you guys all know this, right? 1 over ABC is 2 times the integral 0 to 1 dx, integral 0 to 1 minus x dy, 1 over 1 minus a x plus by plus c 1 minus x minus y cubed. Okay, so I can combine these denominators here using this nifty little Feynman trick. But then I'll have terms which go like k dot p when I combine the denominators, right? So, because from this guy I'll get k dot p and p squared. Of course, p squared is 0. It's a gluon momentum. So I can shift the momentum to find k prime equals k plus px minus qy. All right? So far, completely easy peasy, right? Okay. So the 1 over the denominator, this goes to integral dx dy over k prime squared minus m squared, oops, this chalk sucks, mh squared xy. Okay. All right, so the denominator is symmetric after making this transformation. So now all I have to do is take the trace of these guys and shift the momentum. Okay? So, kind of fun. Okay. So, okay. So the amplitude then, after I take the trace of the numerator, goes to minus 2 gs squared. This 2 comes from the fact that trace TATB is a half delta AB, and then I'm going to sum over the A and the B, which gives me 8. Okay. Let's see, did I skip a 2? Where did my 2 come? Yeah. Then there's an m squared over v. Okay, so this is actually, you get 1m from the trace over those propagators and 1m from the Higgs-Yukawa coupling, delta AB. Okay, so this dnk prime over 2 pi to the nth, integral dx dy. And in a few minutes, you'll see why I'm doing this in gory detail, because you actually get a lot out of this. You get a g mu nu m squared plus k prime squared 4 over n minus 1. I'll tell you where that comes from in a minute. Plus mh squared xy minus a half. Let's see, this is the parentheses that goes with g mu nu plus p mu q nu. I got that backwards. It's got to be p nu q mu. Sorry. All right. 1 minus 4 xy. Okay. 2 dx dy, oops, 2 over k prime squared minus m squared plus mh squared sorry. mh squared xy. P. Okay. Epsilon nu of q. Okay. So there's nothing tricky here. It's just algebra. Okay. So how did this term come? It's because when I have a symmetric denominator, we can take k mu, k nu with the primes, goes to g mu nu k squared over n, where n is 4 minus 2 epsilon, okay? So you can just pick out the symmetric piece. Okay, so here we go, dnk prime. Okay, here's the symmetric denominator, and here's a k prime squared. You can look it up in your favorite field theory book to do this, right? What the answer is. And what happens is actually really interesting. Okay. And we're almost at the end, showing that this is not so complicated. Okay, so what you get, just doing this, dnk, is that the amplitude goes to minus alpha s squared m squared over pi v delta ab g mu nu minus p nu q mu integral dx dy 1 minus 4xy over minus mh squared xy. Oh. Okay, so we looked up the integrals in Peskin, and we left them here in terms of dx dy, and we see that some interesting things happen. Wait, somebody's going to tell me that the units are wrong because I was writing too fast. You were going to tell me that, weren't you guys? Yes, good. Glad. I'm always glad to see people are awake. Yes. Thank you. mh squared over 2. Did I copy this right now? It is alpha s because I am doing the amplitude. Yes. And you saw that because this is a gs squared making an alpha s. Yes. Okay. Now, do I have everything else right? Oh, you want to know where the brackets go, huh? Which one, the first one or the second one? Oh, let me see here. This is... the square bracket is g mu nu. Yeah. Yes, I think I got it. Yep. Yeah, so far so good. Yeah, algebra is hard. Okay, but we've already learned something kind of interesting from this, right? Okay, first of all, we see that this m squared here comes from the Yukawa, and it comes from the trace over that triangle. Because if you write down the trace of the triangle, there are 3 propagators, right? And then 2 gamma matrices over there. Okay, so there are 5 things. And you know you've got to have 4 things when you're doing the trace. P/Q/M/ whatever. So you get a factor of m, which comes up. Okay, there's an m squared. And now if you look at this thing, there was m squareds in the numerator here, right? And the m squareds actually cancel. So you don't get any m squareds left over here. The only m squared is the one that's out front. Okay. Furthermore, this has the form that you guys all knew it was going to have before you started, right? Everybody knew I was going to get this answer. You were going to get the alpha s, the m squared, because you can get just by counting, and this form. It had to have that form. Okay? You want to tell me why? I mean, Actually, it's going to come up when I talk about double Higgs, too. Okay, well, those gluons are on shell, right? So P mu dotted into the amplitude better give me 0. Q nu dotted into the amplitude better give me 0. So this is all it can be. This is a spin 0 projector. So it's got to have that form. Okay, so now we're done practically, okay? We can take this and integrate it on Mathematica if we feel like it. We can do it by hand if we think we're super smart. Or if we're super lazy, like I am, you can say, aha, this is M top, 173. This is M Higgs, 125. We'll just expand in the M top goes to infinity limit. So what we'll do, let me go over here because I don't actually want to erase this, is we'll take the limit of this integral as m squared goes to infinity. And we can expand consistently, right? Okay, so we'll take this thing and we'll make it 1 over m squared. Okay, and then the first term is completely trivial. Gives you a third. Plus dot, 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 dot. Okay. So that's the m squared goes to infinity limit. But now something really, thank you for, you guys should remind me to, switch the blackboard so you can actually see what I'm doing. Okay. All right, now you can see it. All right, so this thing goes to a constant as we take the top quark mass to infinity, right? M squared up front, 1 over m squared there, it goes to a constant. Okay, so the first thing you should say is, well, what about decoupling? We've got decoupling kind of ingrained in our bones. A lot of you guys build BSM models, right? And you've got some heavy stuff, squarks, whatever. So it wouldn't make any sense in the world if all that heavy stuff was affecting our physics, right? But here we go. Here we have an amplitude where no matter how heavy that top quark is, it's going to be a constant as the top quark gets heavier. So this appears to violate the decoupling theorem. Okay, so anybody know what's going on here? That's part of it. I mean, the decoupling theorem does not apply for particles which couple proportional to mass. So, which is essentially another way of saying what you're saying. So if you have a theory where the coupling of a particle is proportional to its mass, it doesn't decouple as it gets very, very heavy. So for example, if you have squarks in a SUSY model, they couple the gluons with some, random coupling, G sub s, and some coupling factors. So they decouple, right? Whereas this Higgs particle couples proportional to its mass, so it doesn't decouple. Okay, so we can already learn some interesting things from this, okay? Because, well, let me just square it and give you the answer before I tell you how interesting it is. Okay. All right, so the Platonic cross-section, let me get all my factors here. I think it's fairly common notation, by the way, to use the hats for Platonic. Alpha s squared over 576 pi v squared delta of 1 minus f hat over mh squared plus order mh squared over 2mt squared. Okay. So there we have the Platonic cross-section. Of course, you can do this exactly, and that's what people do when they actually calculate it, because it's kind of trivial. But somebody asked me yesterday, well, how well does it work? So it's actually amusing that alpha s squared 576 pi v squared. The first corrections to this, which I worked out last night, let me get my factors right, 7 over 120. 1 plus 7 over 120 mh squared t squared. So the corrections turn out to be numerically quite small. So this is actually a very good approximation to the cross-section. Okay, so this actually tells you some things about, say, a fourth generation of fermions. People used to like to say, well, we have 3 generations of fermions. Who's to tell us there shouldn't be 4, 5, 6, whatever, right? What do we know? So suppose I try to add a fourth generation of fermions. So I'll add, what shall I call them? Big T, big B left, big T right, big B right, big N, big E left, E right. Okay, so fourth generation of fermions generically. So let's see what this does to this Higgs production here. Well, Okay, so I'll go back here to my large mass limit, because we know these guys have to be pretty heavy because we haven't seen a fourth generation. There are lots of limits. So what's going to happen? What's going to happen here? So, well, I've got my glue goes to H. I've got my top loop going around it. So here's the top loop. It's a 1, right, because it's independent of the mass. So this heavy T is going to go around the loop, right? Give me another one, T. This heavy B is actually going to go around the loop too, because we know it's heavy, plus 1. And that's the amplitude up there, right? So square this. Okay, so if I add a fourth generation of heavy fermions, the cross-section for making a Higgs goes up by a factor of 9. Okay, no can do, right? The measured cross-section is pretty close to the standard model prediction. There's no room for this is B, for a factor of 9 to increase it. There's not even any room for putting a T here, making it times 4, right? So you can't add a fourth generation of heavy fermions just by this simple argument. Well, that's too bad, isn't it? Okay, so what might I want to add to this to mess things up, change it around? Yeah. Uh-huh. I'm just taking the physical mass to go to infinity. Yeah. Yeah. Oh, sure you do. Sure. Yeah, sure. Sure. Well, not probably. It absolutely is true. Because you don't run into perturbativity. So make this guy 2 TeV or something. Right? The things will still be perturbative, and this argument will still work. This is numerics here, really. Because if you like, I can just calculate this cross-section here, just putting in the mass, doing it exactly for a TeV guy. And I'll get exactly that, because this approximation is numerically exceedingly accurate. Okay. So if it makes you happier, you can think about a 2 TeV or a 1 TeV thing. Yeah?
So is it a precise statement that fourth generation of higher fermions is ruled out that their masses from standard model Higgs, but there's still a possibility that
the exact statement I'm making is a fourth generation of chiral fermions, which couples exactly like generations 1, 2, and 3, is ruled out. If I made some screwy model where the fourth generation was really different, then it wouldn't be a fourth generation. It would be a screwy model with something different. And in fact, since I'm glad you asked that, let me show you my favorite screwy model. And let's see, probably there's somebody in the room who's worked on this. So it's not a value statement. Okay. All right. So as people have pointed out, this whole argument rests on the fact that the Higgs gets its mass from the Yukawa, right? Okay, so what if I added a vector like quark? And with complete lack of imagination, I'm going to call it T. So T left and T right. Identical Okay, so I'm going to add a top quark, and I'm just going to say it's going to be an SU2 singlet, SU3 triplet. Okay? That's the easiest thing I could do. So it's a vector-like quark, so it doesn't contribute to anomalies, so I'm free to add such a thing. And in fact, people who build composite models add lots and lots of weird representations of heavy vector-like quarks. But it works exactly like what I'm going to say now. Okay, so let's go back to our scalar potential that we had yesterday. So we had minus L, I guess, is equal to lambda T Q bar left phi tilde T right. Okay. So here's the standard model coupling of the doublet to the top right. Okay? So then the top right is a singlet under all the quantum numbers other than SU3. So Q bar left phi tilde big T right. So I can couple my new quark in the same way as I coupled my standard model quark. I can have a coupling lambda 3 T bar L T right. And then I can have a coupling lambda 4 T bar left T right. Okay? Plus HC, I guess. Plus Hermitian conjugate. Okay. So this is what happens when I start trying to add vector-like quarks to the theory. This particular guy, I can rotate away by redefinition of fields. Rotate away. Just by redefining my fields. But this guy is interesting, okay? You can have a Dirac mass. So I can just write down a term which is a Dirac mass. So maybe I should call this big M or something. Okay. So now we have a scenario where the top and its partner get part of its mass from the Higgs mechanism, from the couplings to Yukawas, but there is nonetheless a Dirac mass with some arbitrary scale, which has nothing whatsoever to do with electroweak symmetry breaking. Okay? So this is a simple kind of model. There we go. Oh. So the physical fields will be admixtures of the fields I started with, right? The little t and the big T will mix through these terms. Yes?
Are we missing a dimension in the lambda 3 term?
Oh, yeah, I just called it lambda. You can call it M. Doesn't matter.
It's a mass. It's a mass.
The lambdas can have masses. These all have the right masses. Yep.
Sorry, can you specify quantum numbers for vector-like quarks?
Sure. This.
Sorry.
Yeah. Yeah. Wait, okay, so we'll call this M3. Doesn't matter. Except it is nicer if things all have the same dimensions. I agree. The reason I'm cavalier is because, like I say, you can rotate this term away by redefining what you call T right. Okay, so T, both left and right, it's going to be an SU3 triplet, just like the top quark. It's going to be an SU2 singlet, because I'm lazy and don't want to add an SU2 doublet. And it's going to have hypercharge of, let's see, I'm going to write Q equals, how did I defined it yesterday, T3 plus Y over 2. This 2 is convention, actually. So it's going to have hypercharge of 4/3 to get 4/3. Okay? And the left and right guys will both have the same quantum numbers. Yeah, okay, so this is T left, T right. Okay. So they're the same, is the point. Yep. And that's a really important point, actually, because that's what allows you to write this Dirac mass term. Okay. And like I said, this kind of scenario arises in many, many composite models with more complicated representations. Okay. Thank you. So it's good to slow me down. Okay, so the physical particles, well, let's call the physical guys T1 and T2. Physical guys. So T1 is the thing we actually measure, and T2 is the other guy. So this is going to be cosine of some angle, which I'll call alpha. T1, let's call it T1 left, times T left, plus sine of some angle, which I don't care about, times T left. Is this legible here? Kind of? Yeah. All right. Well, but you guys all get the fact that the particles are going to mix, right? So you don't actually need me to write down 2x2 matrices with cosines and sines, because you know what it's going to say, right? Yeah. Okay. So the physical particles are admixtures of the two guys. Okay. So then you can go through, after you diagonalize your 2x2 matrix, which we can all do, and then you can take the physical particles, this T1 left, T2 left, and figure out how they couple to the Higgs. Okay? Everybody knows how to do that, right? We just rotated stuff. But actually, this is really, really interesting because it's completely different from these chiral quarks. Because what happens, and I actually want this to be legible. So here's H going to T1, T1 bar. This is MT1 over V, just like in the standard model, right? The mass over the V. But then there's a cosine squared, what do I call this thing, of an angle here. And if I'm super energetic, I can calculate how this cosine and this mass are defined in terms of the Yukawa couplings, but it's not very interesting. But I can do it. You can do it too. It's easy. Okay, and the coupling to the other guy, which we're going to assume is the heavier guy, T2 bar, is going to be its mass, MT2 over V, times the sine squared of an angle.
Sorry, can I ask really last question? So in this physical state,
Yeah?
does this really have a well-defined SU2 quantum number? One has a double-edged structure, the other has
Well, I've broken that, right? I mean, we're no longer using the doublet, right? It's a broken symmetry, right? You break the SU2 when you give the Higgs of F. Just like in the standard model, right? In the standard model, the left and the right-handed guys have different, when I start out, they have different SU2 quantum numbers.
Yes.
Yes. So this is exactly the same.
But it's spontaneously.
Yes, the spontaneous symmetry breaking actually happens identical to the standard model, right? So this doesn't say anything really about the Higgs sector, right? Because I'm just coupling the fermions. So my theory is spontaneously broken, leaving only an unbroken U1.
Yes.
Right, so this is exactly the same as the standard model Higgs coupling to TT bar. Yeah, because the SU2 symmetry is broken. You don't sound convinced. Think about it and come back. But I'm claiming it's just like the standard model. Yes?
Does TR get rotated similarly to the
yeah.
cosine squared?
You can pick your parameters here. Okay? So you started out here. You could see that there are 4 parameters in that Lagrangian, right? Okay, so I can pick my physical parameters to be whatever I want. So I will pick my physical parameters to be MT1, MT2, cosine theta right, and cosine theta left. Okay, that's what I'll pick them to be. Okay, so let me put a left on this guy.
Oh, I see. I think the mixing angle
Mhm.
sort of spurious, which has a transformative property, such that each part has the same SU2.
No, the mixing angle is just a mixing angle. It's a function of those Yukawa couplings, and I'll just write it down. Mixing angle has no deep significance. Sorry, it's just a function of the Yukawas. Right,
Anyway,
yeah. Okay, so thank you, yes. So count parameters there, okay? 4 parameters to start with, 4 parameters after I'm done rotating things, right? 2 masses and 2 mixing angles. Okay, so the right-handed mixing angle doesn't couple to the Higgs. Okay, that's one way of looking at it. Yeah, because you can choose your mixing parameters in whatever way you find most convenient. I mean, your parameters. You got 4 parameters. You choose 4 when you're done. This is my choice because the physical masses are really what you want to take. And the left-handed mixing angle defines the coupling to the Higgs when you work this out. Okay, so anybody want to tell me why I'm all excited about this? Why this is cool? Why all the model builders really love this?
Now these have coupling theorem.
Well, they couple proportional to the mass. Yeah?
It gets us back to the Dirac part. If you take a large Dirac mass,
Yeah, I'll take the Dirac mass as big as I feel like, sure.
so they can couple it. In other words, the mixture gives a very strong time.
You can make sine theta L is indeed proportional to 1 over m. Sure. Yeah, yeah. But what if I don't want to take m super big? Okay, so let's go back to this argument here. Okay?
Oh, sorry.
Yes?
Just because you diagonalize the masses doesn't mean that you balance out the
Oh, there is a mixing one. Yes, yes, that does. Yes, thank you. There is indeed a T1, T2 Higgs coupling, but that doesn't contribute to single Higgs production. It does, however, contribute to double Higgs production, which I will talk about maybe if I have time and I don't blather too much today. And in fact, for double Higgs production, it's about 15% of the cross-section. So it's very, very interesting. You must have read my life work. Yeah, yeah. Yes. So actually, I should note here, just because it's actually interesting. There is a mixed coupling, but as you can see, when you go to single Higgs production, the mixed coupling doesn't contribute, but it does contribute to double Higgs production. Thank you. And I won't write down what it is because I'll get it wrong without looking it up. It's got some gamma 5s in it. Okay. So, all right, so I'm going to go back here and I'm going to calculate single Higgs production. Okay, so now I've got my my top loop over there, but now the amplitude gets a cosine squared of an alpha, right? And now I'm going to calculate the contribution from my vector-like top partner. We'll call that T1. Okay, T2, sine squared. And this is, of course, squared. Okay, so this is pretty cool. Adding these vector-like quarks basically doesn't mess up Higgs production. Okay, so this is in the large mass limit, so there are corrections which go like 1 over the big masses. But this generically holds true in all of these complicated models with the vector-like quarks. You diagonalize your mass matrix, and sometimes it's pretty hard because you got a lot of weird stuff, and you get a bunch of mixing angles, but it goes like this, okay? So you tend to get the standard model cross-section. So that's pretty cool, guys. So all of you who have written a paper on 750 GeV photon diresonances, I won't ask how many of you have done that, but suppose you wrote a paper on the 750 GeV diphoton resonance, and you wanted to mess around with couplings. You know, you wanted to do something. You could add as many top partners as you wanted without screwing up standard model Higgs production. Okay? Any questions? Okay. So that's pretty cool. At least that, yeah.
Here, MT1, MT2 has large hierarchy, so one is much lighter than the other.
I didn't assume that here. I didn't assume nothing. I didn't assume this. No, I didn't assume anything.
So then if capital M is much larger than M top,
Yeah?
then do you agree that one is much heavier than the other?
Oh, sure. If capital M is super heavy, then MT2 is essentially big M.
Right.
And
Then how do you have overall scaling coming out so that you have nice cosine squared, cosine squared?
Oh, because sine squared goes like 1 over m squared. Yeah, when you work it out. Yes. And that's a really good question because that's how decoupling works here, is that the sine squared of the angle goes like 1 over m squared. Yeah. Thank you. Okay. So, all right. So there we have it. Now we've got Higgs production. So let me see which one I want to. Let's see if I can get it down here. Yeah?
Was there a particular need to set hypercharge?
Oh, why did I do that one? Oh, I was just being lazy. I can take any old representation. But not completely lazy. Suppose I put the top partner in a doublet. Then it would have a B partner friend, right? And that B partner friend would mess up things like Z goes to BB bar because it would come into the loop. So there would be lots and lots of limits. Let me just... So if I were going to have a doublet, left, right, then this new B partner would mix with the standard model B, okay? And then that would interfere with Z goes to BB bar, okay? Because it would get effects from here. And this thing is pretty well measured. So you can play games and try to make this work, but it's much harder. So that's why people tend not to do this. That's why they tend to go to even more exotic representations, is to avoid that. Okay? Yes?
So as long as Higgs production is concerned, it seems to be insensitive to the direct message put by hand.
Yeah.
And is there any channel that is sensitive to this thing? Because I can't see any channel.
Oh, why would I care? No, I don't. That's the statement that Higgs production, you're not sensitive to the mass of the heavy guys. That was a statement for chiral fermions, too. I didn't care if the chiral fermions were 800 GeV or a TeV. They contributed roughly the same.
Right.
Yes. Yeah. So people look for, say, direct production of these guys, because these top partners are colored triplets. So you could have glue goes to top partner, which would have quite a large rate. And that's actually how you would produce it, and then you'd look for it with some scenario for the decay. Yeah. And that's how you get the limits, actually. The limits are somewhere on the order of 800 GeV at the moment, depending on the details. So you just go look for it. Okay. All right. Okay, so now we can just calculate the cross-section for Higgs production. Okay. Yes? What do you mean? Oh, you mean if I add more top partners? Sure, I can add, say, 10 top partners. Okay, so then I add 10 top partners, and instead of having a 2 by 2 matrix to diagonalize, I would have an 11 by 11 matrix, standard model, plus my 10 new top partners, and there'd be a whole bunch of mixing angles, which maybe I could figure out if I were super good with Mathematica, and there'd be a bunch of small mixing angles. But it's a unitary matrix, and this argument relies on the fact that unitary matrices, U dagger U is 1, right? So there would be complicated coefficients for each of these things, but they would be coefficients coming from unitary matrices. Yeah, so and you would get exactly the same thing. Okay, good. So just for completeness, the Platonic cross-section now is my sigma hat, okay? The GG goes to H, and then I've got Z integral Z to 1 dx over x, G of x, G of Z over x, where Z is mh squared over the hadronic energy. Okay. So all I have to do now, it's super easy, right, to get the cross-section, is take my Platonic cross-section, sigma hat, which I just calculated, LF squared over 576 pi v squared, and integrate it with the gluon PDFs. G of x is the gluon PDFs that Matt mentioned this morning, okay? So you can, this combination here is called the luminosity. And notice that this is process independent here, right? This is just the gluons with the resonance cross-section factored out front. Okay, so I can do that and get a number. And let me just give you some numbers. Sigma at 8 TeV is about 19 picobarns. And sigma at 13 TeV is about 44 picobarns. so Matt's guesstimation was pretty close here. Okay, 8 TeV, you get about 19 picobarns for glue goes to H. 13 TeV, you get about 44 picobarns. Notice that going from 8 to 13, you roughly double the rate. So we expect to make lots more Higgses in the coming years. Okay, so now what are we going to learn from this up here, which I carefully didn't erase, because I advertised that this was going to tell us something about effective field theories, right? And so far you haven't seen any effective field theories yet. Okay, so let me, oh, this looks clean over here, so I'll write over here. Okay. So as an aside, suppose I have a term in my Lagrangian, which is G mu nu, G mu nu. Okay? So this is a gluon where I'm going to be lazy about color factors for a moment. Okay. So if I work out just the abelian part, okay? So I'll call this A nu minus D nu A mu, D mu A nu minus D nu A mu. Okay, and the reason I'm being lazy and just doing the abelian part is that this is all that's going to be relevant for where I'm going here. Nothing fancy happens whatsoever if I put in the rest of the terms. Okay, so, okay, for this A field, we'll say A1 has a momentum K1, and A2, say, has a momentum K2. Okay, the derivative term, d mu, is just going to give me plus ik in my Feynman rules. Okay, so I can work out from here, I'm going to get d mu of K1. Let's just work this out. Let's see if I can get my factors right. Okay, so there's a minus because I've got 2 d mu's and 2 i's. Okay, so this is minus K1 mu A1 nu minus K1 nu A1 mu from the first term, K2 mu A2 nu minus K2 nu A2 mu. Okay, so I'm just taking the derivatives here to get the K's. And this is going to give me equals minus 2 K1 dot K2. Okay. A1 dot A2 minus K1 dot A2 K2 dot A1. Okay, so I'm just doing algebra here. And now I'm going to, this guy doesn't come down, does it? All right. Let me go over here because I want you to be able to see this. This guy, yeah, but then I can't put this, can I put this one up? Oh, you fixed it. Wonderful. Okay. Perfect. And it's even clean so you guys will all be able to see it. All right. All right, so over there. Oh. Let me try it. Okay. Let me write it here, and then we'll put it up there, and I'll tell you why this is exciting. 2 K1 dot K2 A1 mu. Okay. Okay. Can you see that? Well, okay. Well, you know what it says, right? Okay, so I start with G mu nu, and I just derive the Feynman rule by replacing d mu by ik slash. And what do I get down here is I get G mu nu minus K1 nu K2 mu over K1 dot K2 from G mu nu. So let's walk over here, and we see the amplitude that I got from GG goes to H has exactly this form, mH squared over 2, which is P dot Q, right, minus P nu Q mu. So it's the same structure as I have from G mu nu squared. So if I started from a Lagrangian, L effective equals minus alpha S over 12 pi H over V G mu nu G mu nu. Aha! If I started from this Lagrangian, so up there's my Feynman rules, put it in the H, alpha S over 12 pi V, go over there, I'm going to get the same amplitude as I get for glue goes to H and the MT goes to infinity limit. So I can get my Higgs couplings in this MT goes to infinity limit from this effective field theory. Okay? And since I actually want to make things SU2 invariant, I'm going to take this to be minus alpha S over 12 pi V phi dagger phi G mu nu. So there we have it. There's my effective field theory for Higgs production in the large M-top limit. Okay, so this is cool. So this gives me HGG, but the phi dagger phi also gives me H squared GG, so there's a relationship between single Higgs production and double Higgs production. Okay, so why is this useful? It's useful because I want to calculate glue goes to H at infinite order in perturbation theory, right? I need to calculate these radiative corrections as I was mentioning yesterday. So here's my glue goes to H. I want to calculate the NLO corrections, which consist of virtual two-loop diagrams, and real gluon emission. So here's NLO. Okay, these have actually been done including all the top quark mass dependence, so we can check this. But what I want to do is I want to use an effective field theory. So I want to, so NLO EFT. I want to use this effective field theory, which corresponds to MT goes to infinity, okay, which gives me an effective GGH vertex. So now I can calculate the virtual corrections. Okay, and it's only one loop. So I've lost a loop when I went to the effective field theory. So it gets easier, okay? And of course, I can check that it works since I know how to do this exactly. So this is very good. But as I said yesterday, when you calculate the NLO EFT, what happens is you get very large corrections and you roughly double the rate. So that says, guys, that you got to go on to the next order to calculate the NNLO. Okay, so yeah.
So NLO has another diagram.
There are lots of diagrams.
Right. So how would you capture this NLO diagram? This NLO EFT, I would assume it will only capture the glue.
That's exactly the point. Is that that effective field theories don't work diagram by diagram. They work by the matrix element to the matrix element. So you can't make a one-to-one matching, right? So this EFT gets the MT goes to infinity limit of GG goes to H amplitude. So you cannot do diagram by diagram. You calculate with the NLO here all the diagrams, and you calculate over here all the diagrams. In fact, there are only two. Okay. So you capture it from the effective field theory. So this is my effective field theory, but it doesn't go diagram by diagram. Yes.
Two questions. First, would that be a V squared denominator?
Nope. And the reason I know it's not a V here, this one is. This is, yes. It's always H over V. That's V. This is V squared, right? Because when I expand, yes, thank you.
The second is regarding the comment on whether there is a diagrammatic correspondence. It seems that when you look at an EFT diagram, when you look at the diagram in the full theory,
Yeah.
you contract the top loop,
Yeah.
point, and then that will give you an EFT diagram. So why isn't there?
Because look at it. That's a really good question. Okay, here there are only 2 diagrams, right, in the EFT. Here there are gazillion diagrams.
Oh yeah,
I mean,
it's not a one-to-one
it's not a one-to-one correspondence. Yeah.
Wait, you only did the three-level matching to get this effective field theory.
Yes, yes.
Of course, this diagram cannot be captured by this effective field theory unless you do one loop matching.
Well,
Yeah.
yes, there is indeed a one-loop matching term, and I could tell you what it is, but I didn't work it out here, and there is a one-loop matching. Yes, yeah. And the one-loop matching is essentially the mass anomalous dimension, which, yeah, I could work out for you in a bit. Yeah. Right. So the point, for those of you who didn't follow the exchange, is this is a tree level term, but now, of course, as I use the EFT to higher and higher orders in perturbation theory, I get corrections to this coefficient. So if we call this, let's call this coefficient, I don't know, C0, then I will get corrections to this, which will be alpha S over pi C1 plus alpha S squared over pi C2, where these C1s and C2s have zeta functions and stuff like that. They don't depend on the properties of the process. So yes, there's a matching. Yeah?
Another question. So it's not obvious for you why we can write the first half of cross the theorem because we're integrating out the top explicitly.
It's an assumption. You can do it either way. You can do it either way. Take your pick. This is what I derived. I integrated out the h. This is an assumption that the h only enters in as phi dagger phi. It's an assumption. Yeah, absolutely.
But in the broken case, that's not necessary.
It's an assumption. Yes, this was my point when I was talking about EFTs. You can assume that the h only enters in SU2 invariant quantities, or you cannot assume it. It's a linear versus a nonlinear EFT.
Well, that's why it's not explicit, right? Yes, it's variance by integrating out the model. You can integrate out new physics, technical physics, and that is also
Sure.
and you can assume linearity in the EFT, but now you're integrating out.
I'm the first to say this is an assumption. This is what I demonstrated to you. This is an assumption. It's a very commonly made assumption, but it's an assumption. Yeah. And let me continue. The only point of this assumption is it relates double Higgs to single Higgs production, which might not be the case. Yeah. Yes, in the back there? Nope, I've integrated out the top. I have a theory with no top. This is my theory. The top is gone. History. Never going to reappear. Yeah. It's gone. No can do. And you know why? And that's because, let me explain why. Let me try up here. Okay. Okay. All right. Okay. Okay, so I get these huge corrections here in this EFT, which tells me I need to go to NNLO. Okay, NNLO. I don't know. What do you want to ask?
So I'm still confused about how that diagram is here. Because think about that.
Which one?
The first diagram at NNLO.
Yeah?
Think of the photon then and stuff like that. I understand it's suppressed, but that photon diagram is never included in
The photon isn't here. Nope,
Right, but
no photons.
If I replace that photon by gluon, it should still not be included here.
No, it is included. It's got everything.
It's the same topology, the photon and the gluon, and the photon is definitely not included.
Well, that would be a mixed QCD. This is an effective Lagrangian that smooshes. It gets everything, just by symmetry. It's everything. It's G mu nu squared. Maybe we can talk later, because it really does get everything. It does get everything.
Yeah, once
You just smush it. I've got a new theory, and my new theory is SU3 gauge invariant, and it's just the GGH blob. Although, in fact, there is, when I put in the non-abelian pieces, there is, of course, the 3GH blob, too, right? Okay, but now I want to go to NNLO. And for sure, I don't know how to do that, including top quark masses. Because at NNLO, okay, so in my effective theory, okay, it's two-loop in my effective theory, okay? And as you pointed out, you need matching conditions to NNLO to that Lagrangian. Okay, but we can do this to NNLO. People have done it because the point is here, there are no mass terms in these loops. So they're all massless two-loop integrals. All these massless two-loop integrals have been categorized in terms of so-called master integrals, and they're all known. And it's because there are no masses. If I tried to put masses into this, there would be bits and pieces that I wouldn't know how to do. And in fact, that's the sort of forefront of NNLO calculations, is doing processes which have multiple mass scales. Okay. So this has been done to NNLO using this effective theory. And you guys might say, well, how do I know that that even makes sense? Gosh, guys, right? You calculate it, we've taken the top out, and you think that maybe there's some subleading top quark effects, which might be important, right? I mean, we're integrating over a bunch of stuff. Okay, so the way you test this, which is extremely useful, okay, is you're calculating some crazy diagram in the real theory. Okay, so let me draw some diagram in the real theory. Let's see here. With a gluon and a gluon. It's something really gross, right? When I'm calculating to NNL. Glue goes to H. Here's a top quark loop. This guy's a three-loop diagram, got a bunch of masses, don't know how to calculate it. So how would you try to verify this? Well, you can generate all the diagrams using fancy computer codes, and the way they test this is actually kind of interesting. So if this guy is, say, P coming in, we'll call this guy K, the loop momentum, and you're going to have propagators that look like 1 over K squared minus M squared, where M is M top. And then from here, you're going to have 1 over K plus P squared minus M squared. And then there's a bunch of other stuff, right, from this complicated diagram. And what you're going to do is you're going to write this as 1 over K squared minus M squared. And you're going to write this guy as 1 over K squared minus M squared. And then you'll have 1 minus 2K dot P over K squared minus M squared plus dot, 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 dot. So we'll just expand in small powers of the external momenta, K dot P here. So the external momenta is small relative to the denominator. So you just expand as far as your heart desires. Okay, so then when you do these traces, you get a bunch of K's in the numerator. But in the denominator, you've always got symmetric integrals. So you reduce it to K squared minus M squared, and similarly for all the other loop integrals. So the denominator is symmetric, so you can symmetrize the numerator. It's just like before when I said K nu was K squared over N times G mu nu. It's exactly the same trick. Okay? So the folks that did this calculation took this and numerically expanded all their propagators like this to verify numerically that these two things work, that this effective field theory actually reproduces the exact calculation to within a percent. So it's a real tour de force. Okay? Yes?
So you just assume that P is
Yeah, well, we know what P is. We know that P dot Q is MH squared, essentially, and P squared is 0. Yes. And so this is the limit. Remember, we're always working in the MT goes to infinity limit.
Right.
So you've always got a 1 over M squared downstairs. Right? And then you just expand out as far as you want to do it.
Just to make sure that effective vertex is the 3-level matched vertex.
Oh, no, here you would have to match it to NNLO, right? At each
consider yet additional NLO diagram in addition to the matching? Or
No. So you match to get an effective field theory where your vertices are exactly that GGH and the GGGH. And it's alpha S over 12, alpha S over 3 pi, and then they're corrections, finite corrections, alpha S squared over pi times zeta 17 or something. It's just some number.
Okay.
So, but the form of that effective field theory is the same.
Right.
Yes.
Right.
So then you calculate in the effective field theory, and then you say, gosh, guys, does this make any sense? So you numerically expand all your propagators to see that it works. So now the folks who just did n cubed LO, one more n here, okay, did exactly the same thing. They used this effective field theory. They did the matching to n cubed LO, which just gives you constant corrections. And then they numerically expanded their propagators out to the 36th term. Okay, wow. Okay, so it was all numeric to get it. And what they found was that this expansion after about the 8th term was super flat. I mean, you didn't have to go much further. So this is a real tour de force.
There's no like beautiful way to
I don't know. I think this is kind of beautiful. Beauty's in the eye of the beholder here. Beautiful. Well, at NLO, as I said, you just calculate. We can do two loop diagrams, 2 to 1. They're resonance processes. You can just do it. And in fact, Michael Spira did it 20 years ago or something. And then, so then you can check it at that order. But once you get to NNLO, it's only numeric. You know, we just don't. Right, that's, okay. So you say, well, this is kind of nifty, but you feel a little bit swindled here, right? And let me point out a few, in the last 5 minutes, a few reasons why you might feel a little bit swindled. Let me see, yeah, I'll go over here. Because I'm really going to swindle you in my next lecture. So you guys need to keep your faculties up and going here. Okay. So we got this effective field theory, G mu nu H. Okay. So I want to use it. Well, the Higgs, as I've discussed here, is produced with no PT, right? GG goes to H. And experimentally, you actually want to see some PT here. So GG goes to HG. Okay, so here's GG goes to HG. Okay, this is the next process you might calculate for Higgs production. So there's some PT from this outgoing gluon, which gives you a jet in the Higgs, and this will help you to tag what you've got here. Okay, so you can just calculate these guys, right? It's a one loop diagram. Okay, so this is a top quark. And just like in GG goes to H, the B quark doesn't actually make any difference here. Okay, so now you want to calculate, guess what? Radiative corrections to this, right? So you say, aha, those two loop diagrams are too hard to do. Okay, so you want to calculate stuff like this, whatever. Okay, but now you have a process which has MH, okay? It's got S hat here. It's got T or PT squared. It's got the mass of the top. Okay, it's got more than one scale. When I did glue goes to H, the only thing I had in my theory was the ratio of MH to MT. But now a 2 to 2 process has energy in the final state. So I try to calculate the radiative corrections to this using my EFT. And it doesn't work so well, because what you get is sigma GG goes to HG equals, let's call it sigma lowest order, 1 plus alpha S. And then you get corrections which go like S hat over MT squared. So you get corrections which grow with the partonic energy. And there's no getting around it. So it doesn't work very well. Okay. So with that thought, I'll stop here, and then on Thursday, I'm going to continue from here and show how this very simple theory, GG goes to H, can be used to measure the Higgs mass, or the Higgs width. I haven't talked about the Higgs width, but it's super narrow. It's 4 MeV. Okay, the resolution of the detector is a few GeV. So the width is narrower than the resolution of the detector, and we used to say, well, gosh, we don't know how to do it. But because of some clever ideas from processes like this, we actually have some new results. So let me stop here, and I'll answer questions and discussion, but it's lunchtime. Okay, thank you. Okay. Yeah. Right.
So can
Yeah.
I confirm this again?
Yeah?
So this is effectively two-loop diagram.
That one's a 3.
Oh, three. Oh, okay, sorry. So effectively, I might say, I want to have effectively three loops size of the effective.